Welcome to the Flower Quick Start tutorial using PyTorch. Flower is the best framework for simulating and deploying AI workloads. You can think of federated AI as a type of distributed AI where the data cannot be moved. It cannot be preprocessed in advance. It cannot be many times inspected because the data is private. Typical scenarios that meet this criteria are, for example, networks of hospitals within the same country or across different countries that they want to collaborate to train a single model, for example, a model that can detect problems on X-ray images. They want to train the model all together to take advantage of all the massive amount of data that is distributed, but they don't want to share the data with each other or centralize that data in a single place and then do the training over there. Another example is a network of banks. Maybe they want to train a single fraud detection model, but these banks, they don't want to share with each other their transactions data for obvious reasons. And there are many more examples where federated AI is the best, and in many cases, the only way of leveraging data that is distributed cannot be accessed. In this video, I'm going to show you how you can start with Flower and develop your very first Flower app, and you will see how easy it is to run it in a simulation environment. And I'll show you at the end of the video how you can take it even further and run it in deployment, which means involving real physical devices. So starting with Flower is really easy. There are only 3 simple steps. So the first step might sound very obvious, but is installing the Flower package in a Python environment. This can be done by doing pip install flwr. Once it is installed, you can use the Flower new command. With Flower new, you will be able to create a Flower app based on some of the built-in templates that Flower has. There are several built-in templates. Each template is designed with a particular ML or AI framework in mind. For example, there is a PyTorch template, there is a TensorFlow template, there is a JAX, MLX, Hugging Face, and so on. In this tutorial, we will look into the PyTorch template, but all templates are very similar. Once you have a Flower app ready out of your template creation process, you don't need to change the code or even inspect the code if you don't want to. We will see very soon how you can directly run it right away with the simulation runtime. And this can be done with flwr run. Without further ado, let's see how this can be done. So here I have my terminal. I'm in a new Python environment where there is only basic dependencies installed. If I want to install Flower, I will just do pip install flwr. Flower is a very lightweight package, so it takes no time to download and to install. Once I've installed this, what I can proceed and do is create my Flower app. For example, I will be doing, as we saw, Flower new. And it's going to ask me, please provide the app name. And here you can pretty much use any name for your app. For example, I'm going to call it my awesome app. And then it's going to ask you what's your username. This is not, there is not a big thinking behind this. You can just type your name or any random string. What I did is just type my name. And then I'm prompted with different options of different templates I could choose from. As you can see, there are many templates: PyTorch, TensorFlow, Scalar, Hugging Face, and others. Currently, the current version of Flower is 1.21, and we are in the process of upgrading all our Flower apps to a new abstraction that we call the Message API that makes writing apps so much easier, and it brings you a lot of more versatility on what your apps can do. And currently, only the PyTorch app has been updated to the Message API. In the next release, Flower 1.22, that will come out in less than 2 weeks' time, all of them will be updated. So for this tutorial, we're going to work with the PyTorch template, so we're going to use the one that is already updated. So I will choose the template with the number 1, which will be this one. And once that's done, I'm shown a series of instructions that I can follow to run my app. So for example, I'm told, okay, cd into your app directory, and then pip install it. Why do we want to pip install? We want to pip install because every app is comes with a set of dependencies. For example, the PyTorch template comes with Torch and Torch Vision dependencies. So I will just do pip install -e. So whenever I make some edits to the code, those are already taken into account. And then if I want to run my app, remember what we had to do. The only thing we had to do was to execute Flower run. So that's what I'm going to do. And now it's going to start. And we will jump into the code very soon. But what you can see right from the beginning is, well, there is some logging process going on, and I'm shown some metadata about what my run is going to do. It's going to run fed_average, which is a way of an algorithm for federated learning. It's going to run for 3 rounds. My model is fairly small. And here I can see other type of configuration relevant for federated learning. And it has already finished because it was a very lightweight workload. And what we can see is that on round 1, 5 out of the 10 virtual nodes were sampled. The training loss at that point was 2.11, followed by the training round. There was an evaluation round where the model is evaluated on the local validation set of every client. And at that point, because it's very early on, we see a validation accuracy of almost 0.1, which is a random guess. This is using the Cypher10 dataset. And as the process continues, we can see that the validation loss gets better and better. Before diving more into details of what all this means, let's take a look at the code. So if I open VS Code, I will see that there is a subdirectory called my awesome app, which contains 3 files. In this case, let's inspect first the server app. So the server app runs 2 main functions, 2 main concepts. First, we want to initialize what will be our global model. So this is the starting point of the model we want to federate. In this case, we're going to be federating a small CNN. That is, if we inspect it, it is fairly simple. It's a CNN from one of the most common PyTorch tutorials. So we want to federate that model. What we do is we construct an array record object, which is a special way of representing arrays that Flower uses. And then we're going to define what's the algorithm that we're going to be using to orchestrate the entire federated AI process. In this case, we're going to use a strategy that is called fed_average. And what it does is relatively simple, but works pretty well in many scenarios, which is it will sample a subset of nodes in my federation, and that can be controlled by this argument. Each node will receive the same copy of the model, in this case, at the beginning, the randomly initialized CNN, and every node is going to train that model with their own local data for a number of epochs. In this case, it's going to be only 1 epoch. Once all those clients nodes finish training, they're going to send the model back to the server app, in particular to the strategy, and the strategy is going to aggregate all those models. And as the name implies, what's going to happen is the aggregation is going to be just a weighted average of all those models received by clients. And that weighted average will become the new global model. And then a new round will start. And over time, across several rounds, sometimes many rounds, the model converges to a pretty good accuracy. So here we define our strategy. There are more strategies you can choose from in Flower, but fed_average usually is a good starting point. Once we have it defined, we can just start the federated learning process. And if you are curious on how this loop of actions that results on round 1, round 2, round 3, you can inspect how the start method works. So this is the server app. Pretty much 2 things you need to do. Define what the global model is, choose the algorithm for orchestrating the federated learning process, and then start it. Now let's look into the client app. So the client app is fairly simple as well. A client app can define different methods. We're going to look into the train method. And the signature of these methods are always the same. A message comes, and there is a context. The message is a payload that has been sent by the server app that will contain the model that we want to do local training with, and other configurations, like maybe, for example, the learning rate that the client app should use at this particular round, if we want to do some form of learning rate decay, for example. In this case, we get the model from our message. We convert it back into a torch static because we're using PyTorch. So we have these built-in conversions in Flower. At this point, our model is exactly the same model that the server app had at that particular point in time. Then we load some data. In this case, we are using the simulation engine, so we are using another tool from Flower called Flower Datasets to partition and load a specific subset of the, in this case, Cypher10 dataset. So we use this function to load, for example, the 8th partition of the dataset out of n partitions. In this case, we are using 10 partitions because there are 10 clients, as you can see. And we only use the partition that corresponds to this particular client, which is defined by the partition ID. And then once we have the data, train loader, once we have the model, what this train method does is simply call a very standard PyTorch training loop. At this particular point, there is nothing really different from the way you might have already used PyTorch in other examples or other projects you might have run. For example, if we inspect the function, we can see that, okay, we are ensuring the models on the device we want to use. We define our criterion, our optimizer, and we just do backpropagation for a number of epochs. All this looks like pretty standard PyTorch code. If you were choosing a different type of framework, you would follow the particular way of doing training with such framework. And once the training is completed, what we need to do is to reply back to the server app, more concretely to the strategy, with a locally updated model and any other metrics we might want to aggregate. For example, the training loss, it could be the training accuracy or anything else. And also, very important, we indicate how many training examples or how many batches were used by this client. And this is going to be used as a weighting mechanism to do the averaging of all model updates. And the model, as I said, is constructed as an array record object, and then everything is bundled again into a message. So you can see that we are returning a message, which is exactly the same data structure that we received in this function. If we inspect very quickly how the evaluate method works, I'm not going to go line by line, but the idea is exactly the same. We have received a global model from our server app that we want to, in this case, evaluate on the validation set of this client without modifying the model. So we do the same thing. We materialize the model, apply the weights, load the validation set of this client, and then call a test or evaluation function, which looks like this, like a standard way of doing it with PyTorch. And then what we reply is not an updated model because, again, we haven't modified the model. We reply with some metrics of interest. In this case, the validation loss and accuracy. And again, the number of examples, so we can aggregate these metrics correctly. So now you can see that at the end of a round of training, we can see that in addition to aggregating the model, we have also aggregated the metrics automatically, and we get the train loss metric because that was the metric we sent back. And in a round of evaluation, we get these two metrics, evaluation loss and evaluation accuracy. Why? Because those were reported by the client apps in their evaluation method. If you are free to add more metrics if you wish to do so, they will be aggregated as well. So this is how a basic PyTorch app looks like with Flower. You can, of course, customize it to your unique use cases. Maybe this model is too simple for your use case. You want to use a bigger CNN or a vision transformer or an LLM, anything. You can really replace this model with whatever makes sense for you. Similarly, here we're using the Cypher10 dataset, but you can replace it with something that is more interesting for you. Could be a vision dataset or could be anything else. Before wrapping up the tutorial, I want to show also that part of the Flower app, of course, the main components are the client app and the server app. But very important is also this PyProject.toml file, which we haven't looked into. But here it defines what the dependencies of the app are. In this case, Torch and Torch Vision, Flower datasets, which helps with partitioning the dataset and downloading it. And also importantly, there is a section in this TOML file that allows you to define hyperparameters or parameters in general for your run. For example, let's say I want to run this code again, my app again. But I want to run it for, instead of the default 3 rounds, I want to run it with 10 rounds. So I can do it like this directly from the command line. Run config, and then I will do. And why this particular key? Well, because it is defined here. Let's say that I also want to change the learning rate. I could do it like this. So in this case, internally, what is going to happen, you can see here, number of rounds now has been changed to 10. In this case, what's happening is the exact same app is running, but we have overridden the configuration. How those config files are accessed? Well, you might have noticed here in my client app, we can access the run config, which relates to this section of the toml file. We can access it through the context. For example, I can read the local epochs. For the learning rate, I could have read it from there as well, but because of different reasons, if you want to do, for example, learning rate decays based on the round number, you might want to send that value from the strategy instead of reading it directly. This is more relevant for more advanced usages of Flower. And finally, I want to tell you a little bit about these sections of federations. So there are 2 ways of creating federations in Flower. One is for the simulation runtime, and another one is when you want to actually deploy your app on real devices connected in a federation. In this case, you can see that we have 10 supernodes. This means that there are 10 virtual clients. What if we wanted to have a federation with 100 virtual clients? Well, it would be as simple as doing this, and without having to change anything in the code. For example, I can just run it like that. Instead of running with the default 10 clients, now everything transparently scales to the number of clients we chose. And instead of choosing half of them, instead of choosing only 5 per round, now we have half of them, which is 50 per round. And one of the more immediate observations is that now we have many more clients, which means that unless we make changes, the data partition each client has is much smaller. So training becomes a little bit harder. And you can see it here already. After 3 rounds, we got to 16.5% validation accuracy, where before we had it, I think, over 20 or over 30%. So this is everything I wanted to show you about how to use Flower and how to start with Flower. This was a quick start PyTorch tutorial that you can find in the documentation as well. If you want to take this even further, I encourage you to take a look at the advanced PyTorch example on our GitHub. There you will learn how to not only use a strategy, but create your own strategy. And you will be able to also learn how you can embed a weight and biases logging. So all these metrics we saw on the terminal can be logged to your own weight and biases projects. And you will learn also how to create other type of partitioning schemes for your datasets that might make it a bit more realistic. You can also take a look at the embedded devices example. There you will see how you can run another PyTorch app, very similar to the one we had here, but you will learn how to run it in deployment. The process of running things in simulation and deployment are really identical. You will use Flower Run as well. But in that case, you might not have you wouldn't be using Flower datasets to partition your data. The data will be pre-partitioned beforehand, and you might want to ensure that each of the connected devices has some type of data that is relevant for the app you want to run. Everything is explained in the example, so go take a look. So this is everything for today. Here we are only looking at PyTorch, but again, Flower is framework agnostic. You can use it with any other type of tool you want, and there are many examples using those other packages. If you have questions or you would like to chat with other members of the Flower community, I encourage you to join our Slack channel. We are getting close to 7,000 people, which is, I think, a big number. And also take a look at Flower Discuss, where we have longer discussions about how to do things with Flower. Okay, thank you very much for watching, and I wait for you in the next tutorial. Bye.